Continue with the slide 20, example 4, finding an initial basic feasible solution. With the standard linear programming simplex method, finding an initial basic solution is just setting the original variable, most of them to 0, and since that's their lower bound by default, and using the slack variable on an artificial variable to start an initial basis. But once if some of the original variable has a non-zero lower bound and non-infinity upper bound, so this could be problematic. So let's take an example to see how we're going to fix this situation. For example, this is my an example. Maximize ax1 plus 10x2 and x3 and x4 and x5 are the slack variable, and surplus variable, respectively. And x1 is between 1 and 4, x2 is between 2 and 6, 3, 4, 5s are non-negative restriction. So this is standard. Supposing we set x1 equals to 1 and x2 equal to 6 as either one of them lower bound, one of them upper bound. Now we're going to see what happened, the slack and surplus variable as a starting basis, okay? x1 equal to 1, x2 equal to 6, going to get x3 equals to -1, x4 equals to 2, and x5 is going to equals to -10. So therefore, it violates these non-negativity constraint on the slack variables x3 and the surplus variable x5. So what do we do basically in this situation? So we basically multiply the first and the third constraint by -1 and force them the right-hand side to become a positive value to begin with. So what we do is adding of artificial variables, x6, okay, right here, since I multiply this constraint by -1, my right-hand side becomes negative, so I'm adding a artificial variable x6, and this we already have x5 from -1 becomes +1. We do have a identity initial basis, but the right-hand side is still negative. Okay, and this x6 is the artificial variable, and our case is trying to get rid of them. Since we're maximizing, we're using two-phase method to begin with. It's using only x6, negative x6 as my objective function. My main purpose is get rid of x6, which is artificial variable, so I can find my initial feasible solution. Okay? With that, again we set x1 equals to 1, x6 equal to 6, x2 equal to 6. Now the current feasible solution becomes x3, x4, and x5. x6, x1, and x5. It will be 1, 2, and 10. And they all positive right now. All right. 1, 2, and 10. And my objective function value equals to -1. Now I can start my initial tableau. Okay? And that's initial tableau. I have a feasible solution to begin with, on the right-hand side are positive, and here we can start seeing, okay, x1 has a lower bound with a negative zj minus cj value, so x1 is a candidate to enter. x2 currently the upper bound, but has a positive zj minus cj value. x2 can enter. x3, however, is lower bound with a positive zj minus cj value, and therefore x3 is not a candidate to enter the basis. So we can choose either x1 or x2 to enter. Basically, we can start our process right now. So I'm going to stop this part of the example 4. Is just illustrate how to find a feasible, initial feasible solution to begin with and start a tableau. And then we can continue using the bounded variable revised simplex method. Okay, thank you very much. This concludes our lecture 8, and we'll see you next time in lecture 9.